In this video, we're going to talk about dependent compound events. Remember yesterday when we talked about independent events, those are the ones where there are two events that are put together, but they have no effect on each other at all. Whether it's spinning a die, or spinning a spinner and rolling a die, or taking something and then replacing it or putting it back. Today's video in dependent, we're going to see how this one relates. So we have here the same example from the independent video with the socks, and we want to know the probability of you choosing a red sock. You keep it, and then you choose a white sock. So the big word that has changed this problem is this phrase right here, to keep it. You have originally in your drawer the 12 socks, and out of those 12 socks, 2 are red. But when you keep one of those red socks, you now have a total of 11 for the second probability to choose from. So with that total of 11, you still have the 3 white socks because you didn't pick a white sock, you picked a red sock from the first hand. But your total is now different. It's still compound probability because you have the word and then that then word. It means to multiply. So we can do here, again, simplify this out. This is technically our probability, but again, we want to simplify fractions where possible. So 2 twelfths is 1/6 times, and 3 elevenths can't be reduced. They're both prime numbers, so they can't affect each other. But we can cross simplify. 3 and 6 have a common factor of 3. 3 goes into 3 once, and it goes into 6 2 times. So when we multiply this out, we have 1/22. Now, if you go back and compare this exact same example from yesterday, where it was the same one except we did not keep the red sock, that probability was 1 out of 24. This probability has now changed because of the fact that I kept the red sock and did not put it back. It changed my total to 11 now, and so there is more likely of a chance of getting a white sock out of 11 socks than it would have been out of 12 socks. And that's what dependent probability is here. Since the first sock was not replaced, choosing a red sock on the first try did affect the probability of choosing a sock in the second try. Therefore, these are dependent. I want to talk about some other words that we can have. We've talked about did not replace. We can say stuff like did not put back, or kept would be a good one, or to keep something. Even if you're dealing with food and you eat something or drink something, so if you had sodas and you drank a soda and then obviously you can't put that back because you drank it. All of these types of words in essence means that you do not put it back. And so what happens is that first event affected the second event. It changes slightly from independent. We do have it to where the first outcome affects or changes the outcome, so that the second probability is affected or changed. It's still the same thing if you look right here. It's still the same where we have our word and, which means multiplication or to multiply. But this second event right here is going to be changed depending upon what we did on the first event. So to give you another example, in a shipment of 20 computers, 2 are defective. So that means 2 are defective, or broken, so I'm going to put defective. And that means 18 are fine, so they're not broken or anything. So I'm just going to write that down. 2 computers are randomly selected from the 20 and tested. What is the probability that both are defective if the first computer is not replaced after being tested? So again, because it says both, we know this is going to be a compound probability. We don't see this word and anywhere to let us know that we're going to multiply, but because it says both, we know it's compound, and compound is always multiplied. So the first event is just like a normal probability. We have 20 total computers, and out of those 20, the 2 are defective. So the first one doesn't get changed. It stays the same, just like we've been doing for the last couple weeks with probability. The second one is what gets changed. If I do not put back that defective computer, that broken computer, that means now I have 19 computers to choose from to test. Not only does our total change now, but if I kept one of those defective computers, that means one defective computer is left over. So this is one where your numerator and your denominator are affected. In the socks example, only the denominator, the total, was affected. But here, our numerator is affected as well because I want to know what's the probability of picking both defectives. So here again, because it's a compound, I'm going to multiply. I'm going to simplify this 2/20ths down to 1/10, and then 1/19th, nothing can happen with that. So I have 1 times 1, which is 1, 10 times 19, which is 190. So my probability of picking both defective computers in a row is 1 out of 190. So again, the big thing here is this second probability right here. This is the one that is getting affected. This one did not. It stayed just like we've been doing for a while. But the second one is getting affected. So hopefully this helps you with dependent probability.